All right, so this is going to be section 2.1 of Math 146, video number 2. In this one, we're going to focus specifically on the concept of an even and odd function. Um, so in order to really understand how and why even and odd functions work, I'm going to show you some things graphically. I'm going to show you the actual algebraic way to evaluate these things first, and then we're going to kind of like relate it to the graph. So hopefully it makes sense. So you've probably done this before. For something to be an even function, that means that the function evaluated at x has to be the same thing as the function evaluated at negative x. So f of x and f of negative x both have to be the same. In order for something to be an odd function, well, the function evaluated at negative x has to be the same thing as the negative of the function evaluated at positive x. Okay, and we've probably seen all this stuff, or you've done it at the very least using polynomials, and polynomials are the easiest ones to do when it comes to this specific algebraic method. So let's actually take a look at one example of a polynomial first. And we're going to use this method. So for our first example, let's say that f of x is defined to be x squared minus 5. That's a 5. And our goal is to determine whether this is even, odd, or, as in case of probably most functions, neither. So that's our job, even, odd, or neither. So the very first thing that you should test algebraically is f of x equals f of negative x. So literally that just means we are going to take and substitute a negative x in for every x. So I'm going to place a negative x where the x was in the original function and then simplify. So if I take negative x and I square it, I should get positive x squared. And the negative 5 didn't change. So what we have is that f of x does indeed equal f of negative x in this case. So this would be an even function. All right, let's try one where maybe we're going to get some kind of a different result. Let's try f of x equals, let's go with 5x cubed minus x. So once again, the first thing that we should try is we want to determine whether this is an even function first. So we will do f of negative x. And the reason it's good to try even first is because if you're going to do odd, you're going to need f of negative x anyway. So you may as well determine whether it's even, because if it's even, then you're done. There's nothing else to do. All right, so let's replace every x with a negative x. And since we're replacing x with negative x, I always like to keep it in parentheses. I just think it makes it easier to simplify in the end. All right, so now if we were to take negative x and cube it, well, that's negative x times negative x times negative x. So that's going to be 3 negatives, so we'll still have a negative out of this. So we're going to end up with a negative 5x cubed. And then the last one, we're just literally going to distribute the negative through, and we should get a plus x. Okay, well, that is definitely not the same thing as the original f of x. As a matter of fact, they're complete opposites. So it's not even. So now we're going to check to see whether it is odd. Well, that means we need the negative of f of x. Well, the negative of f of x in the case of a polynomial literally just means you're multiplying every term through by a negative sign. So you're going to get negative 5x cubed plus x. And indeed, that is the same as f of negative x up there in the red. So these two things are the same, which means that this is an odd function. And then let's try an example where, like the one thing we haven't tried is where neither one of those things work. So let's just go ahead and show an example. And again, these are all polynomials. We're actually going to focus on non-polynomials and what all this means in just a second. So let's do f of x equals x cubed minus 1. So again, let's check for even first. So we'll do f of negative x. Let's replace the x with a negative x and then simplify. Once again, the negative x cubed is going to give me negative x cubed. Don't need the parentheses anymore there, and then minus 1. So that's close to f of x, but again, they're not identical, so it's not even. So now let's try the negative of f of x. Once again, that means multiply the original f of x by a negative sign, or in this case, change all the signs because we're multiplying everything through by negative 1. And once again, that's close. I've got the negative x cubed part, but I've got a plus 1 instead of the minus 1. So in this case, this is neither. It is neither odd nor even. All right, so now let's take a look real quick at what this looks like graphically, and hopefully all this algebraic stuff will make some sense. So let's take a look at, I'm not going to use x squared minus 5 specifically, but I'm going to use x squared. We're just going to get rid of the minus 5 because in this case it's not actually relevant. We could use it, but I don't see any reason to. So in the case of an even function, okay, this would be an even function. We're just going to say that this is the graph of f of x equals x squared, your standard parabola, which is supposed to go through the origin there. I kind of missed the origin, but that's the idea. So an even function says that f of x has to equal f of negative x. Well, that just means, so f of x is a function, right? That's a y value basically of your function. F of negative x, again, it's producing a y value in the function. What it is saying is if I take, let's just say we let x be 2. If I take x to be 2, which may be someplace around here, it's going to produce a y value. That would be f of x. Well, now let's say we let x equal be the negative of that x value. So instead of 2, we let it be negative 2. Well, if we go to negative 2, well, you know what? It should produce the same exact y value. So this y value here should be identical. So ultimately what you're saying is it doesn't matter whether I plug in the positive or the negative x value, it's going to produce the exact same y value. And what that does is it gives you symmetry. It gives you symmetry specific to the y-axis. So graphically, that's what you are looking for something to be an even function. It must be symmetric to the y-axis. So knowing your graphs of functions really will help in order to determine whether something is even or odd. Showing it algebraically isn't always the easiest thing to do, but at least you'll know, okay, this is supposed to come out this way if you know the graphs. So you know your standard parabola y equals x squared, or in this case f of x equals x squared, is going to be an even function because it will be symmetric to the y-axis, which is why example number 1 worked, because that function f of x equals x squared minus 5 is the parabola that we see here, just shifted down the y-axis literally 5 units. So that's why it worked out to be even. So again, think of it that way. Positive or negative x input produces the exact same y output, even function. Okay, that's why f of x would have to equal f of negative x for it to be even. Okay, so now let's take a look at what it might mean to be odd as a graph. So sketch another graph here. And we said to be odd that f of negative x would have to equal the negative of f of x. So that means if I were to take and substitute in, I don't know, let's say that we're going to plug in -4 for x. So if I plug in -4 for x and it produces some kind of a y value, I'm looking at the left-hand side here, we'll plug in -4 for x and it produces a y value. Let's say that the y value is up here, whatever that y value is. The other side of that says that if I were to take the same value of x but in the positive direction, so I'll plug in maybe a +4 for x, it should produce the negative of that y value. So instead of going up, it would be down here. And that would be the case for anything. So basically, whatever the x value is that I plug in, whatever the y value that it produces, for it to be odd, if I plug in the opposite x value, it will produce the opposite y value. So something like this, I missed my dot. I missed it kind of in both cases, so I actually didn't do that bad. So if you've never heard this before, the way you graph something, if you miss your dot, to make it right, you make your dot bigger. That's a little hack. Anyway, so that would be an odd function. And what you should notice is that an odd function is actually symmetric, but it's symmetric to the origin. Now, this is really difficult for me to do. But if you think about taking this entire graph and rotating it around the origin, basically, sorry about that phone ringing in the back. But if we were to drop a pin right in the center here, right at the origin, and then we were to take this graph and basically spin it around that pin, so we would take the whole thing and kind of rotate it that way, what it would do is it would, if you rotated or spun it 180 degrees or halfway around, it would lie right on top of itself. So that's the way you would graphically look at something to be odd. Basically, it has to be a 180-degree rotation of itself. So while I can't obviously do this on the computer, if you were to take that, if you were to take your piece of paper, if you sketch this and literally turn it upside down, it would look exactly the same. Okay, that's the idea for something to be an odd function. And I did not specifically write a function for this, but that would be like the second one that we did where it ended up being odd. So for something to be odd, it will be symmetric to the origin. And then obviously, if it doesn't fit either one of the two of those categories, it's not either. It's neither even nor odd. All right, so symmetry to the y-axis is even, symmetry to the origin is odd. And let's go ahead and take a look at something now, which is a non-polynomial type function. For example, what example are we actually on here? I think it's just like example 4, okay. For example, let's take f of x to be the absolute value of x. Now, once again, if you know the graph of this, it really does help because you can think to yourself, oh, this is easy. I know what this graph looks like. But we're going to try and show it both ways. So graphically, most people think of the absolute value function as the v because it kind of takes on that looks like a v. And visually, as long as you know that that is the function, that you should know that that is an even function because it is definitely symmetric to the y-axis. Basically, again, it is saying no matter what x value I pick, if I pick this to be our x value here, the negative of that x value, whatever it is over here, will produce exactly the same y value. Oh boy, did I miss, that was horrible. Let me shift that a little bit. All right, that looks better. So that'll produce exactly the same y value. So let's show the property that we did before. So f of x should equal f of negative x. Well, if I were to substitute a negative x in the place of x, well, we should know that the absolute value of negative x is going to produce a positive value no matter what. Technically, the way you would do this is you would separate this to be the absolute value of -1 times the absolute value of x. And of course, the absolute value of -1 is +1, so it does just simplify to the absolute value of x. F of x now equals f of -x. This is even. All right, let's see if we can figure one out here for a root function. Oops, that should be example 5. Let's let f of x equal the square root of x minus 2. All right. So once again, if you happen to know what this graph looks like, and this is really beneficial if you do, you're going to be able to tell whether it's even, odd, or neither pretty quickly, and then we can try and show it algebraically. So the graph of f of x, first of all, equals the square root of x would look like this. But this isn't the square root of x, it's the square root of x minus 2, which means that it's actually been shifted 2 units to the right. So instead, it's going to look something like this. And hopefully you can visually look at that graph and say, okay, well, this definitely isn't even. It's not symmetric to the y-axis. And it's definitely not going to be odd, because if I rotated it 180 degrees, it would actually look something like this. It's not going to be it's not going to lay right back on top of itself. So this one in this case is not going to be either one. So let's show it. So if we were to take f of -x, well, that's simply replacing x with -x. And there really is no way to simplify that. It's not identical to the first one, so it's definitely not even. And then we would have to do the negative of f of x. Well, that would be having the negative of the original function, which is a negative on the outside, and then x minus 2. And that is not the same as f of -x, the one right above it. So these two things are not the same in either case. So that would be a case where it is neither. All right, and that's the general concept behind trying to find even, odd, or neither. And there's certainly other functions that you could do, but once again, it really helps for you to know what the sketch of at least the parent functions look like for exponentials, for logs, and so on. Obviously, the more complicated those get, because you can produce even and odd functions out of those things if you manipulate them or you composite them with some other things. But this is the general idea, and I think that's probably all we need to do in reference to even and odd. So I think we will end it there. That should be good enough for 2.1.